Welcome back to Launch Window Research. Today we have an interview lined up, but it's not like the others. Instead of interviewing a space industry veteran, we're interviewing the founders of a new startup called Wave Motion Launch Corporation. These two founders met in graduate school and are hoping to bring a completely new technology to the launch industry. Their technology is a method of getting to low Earth orbit and beyond without carrying the propellant on your spacecraft. But it's also not a space gun. So what is it? That question and more will be answered in this video, and if you want to learn more about the company afterwards, there will be a link at the top of the description. But overall, hopefully this interview gives you a better idea of what it is like to be a startup founder in the new space industry. Let's go. Well, Finn, James, it's so great to have you on the channel. Thank you for taking this time out of your day to join us.
Yeah, thanks, Nathan. No problem.
Thanks. This is really exciting. Glad to be here.
So, Finn, you are the CEO, so I wanted to ask you, what you guys are building isn't a rocket, really. It's not a space gun, but it is a propellantless form of space transportation. So how exactly does this technology work if it doesn't fit into the previous categories?
Yeah, what it is, in a sense, is kind of like two rocket engines pointed at each other. So you have your rocket engine on the ground. In current embodiments, it's really just a chemical rocket engine that operates at extremely high pressure. You've just got a combustion chamber. You light off some combustible material inside there, and you exhaust your resulting gas through a nozzle. Now, out of your first rocket engine on the ground, you got your jet coming out. And then in front of it, you place a big nozzle, just a large object that's sort of shaped like a hemisphere. This intercepts the jet, it reflects it rearwards, and then what you have there is your second rocket nozzle, and off it goes. So that's how the current embodiment of it works. And importantly, that's not a space launcher yet. It's just being used for munitions launch. Of course, the limitation of this technology is if you want to go fast, your jet has to be moving at least as fast as your vehicle if you want to impart any thrust to it at all. So that's your big limitation there as compared to regular rocket engines. Anybody can put a kerosene oxygen rocket motor with an exhaust velocity of 3 kilometers per second, and as long as they have enough propellant aboard, they can go as fast as they want. But with us, we've got this issue where we're not going to be moving any faster than the jet that we're generating.
We'll touch on the later form of this technology later, but you're developing two types of jet guns. One is sort of with gas to sort of just launch munitions, but the latter one is going to be a super high velocity Macron beam of some sort. What's the difference there between these two systems?
Sure. So as I'm sure some of your viewers have already intuited, the issue with gas jets is that they pretty rapidly dissipate in the atmosphere. So if you want to accelerate your vehicle to orbital velocity, even if you do have a gas jet that's moving fast enough, for instance, if you use hot hydrogen or something like that, you're necessarily going to be exerting very high G forces on the vehicle, on the order of at least 2,000 Gs. Now, you might ask, hey, why did you even bother to develop the jet gun at all? Well, the nice thing is that it's really, really easy to build, as long as you're not trying to go to space. And it also, and the same advantages that it has over a rocket or a gun in terms of being compact, light, and simple, are also advantages that it has over rockets and guns that are used in the military, not just for space launch. So the jet gun, in addition to being something that has a very low barrier to entry in terms of development work, which is important when you're two broke grad students, also is something that has succeeded in winning us a military contract for development, and something that we see as a source of revenue for the company in the future. Although, as we go further along, we see defense as being a smaller and smaller part of our business.
Of course. So you touched on the potential defense applications of this technology. We'll ask James about that in a second. But what I'm curious about is, considering that you're two broke grad students, I know that you guys have built a prototype and successfully tested it. So what was that experience like, and what have you learned from your initial testing of this technology?
It was pretty tough. It was not very safe. Um, I pissed off a lot of landlords, but at the end of the day, I guess if I could sum it up in a sentence, it was bigger is better. So we used a lot of scrap materials out of the University of Washington dumpster. I think we have 2 pressure vessels out of them. We had to lift those around, hoist them around, take them to various student flop houses in the Seattle area and work on them using some pretty primitive machine tools. Our first launcher was really like a huge spud gun just filled up with compressed air and I think some kerosene with gunpowder and a diesel glow plug for ignition. Burst diaphragms made out of random steel scrap that we took an angle grinder to. It was definitely a pretty tough row to hoe. I had to do a lot of fiberglass layup in a shed with an electric heater. It's definitely impacted my IQ a bit. At the end of the day, what this launcher did was it's really impressive, and I'm sure you can show some videos of it going off. And it was worth it for us in the end to go from having a little prototype, our first prototype, just operating off little 44 Magnum blank cartridges, to this huge prototype that was 3.5 feet long, 2 feet wide, put out 5 or 10 megajoules of energy. I think about 2 meganewtons of thrust, maybe about a gigawatt of jet power for a few milliseconds. And with this huge prototype, and this is an important lesson. A lot of people were saying, you guys are crazy for like going to this scale. With this huge prototype, we could say to the Navy when they became interested in the technology, well, we've already got it working at artillery scale, so why don't you just give us some money and we'll just go the extra step, right? So, which was something we could not have done at all if we were still at the small subscale stage.
Yeah, of course. I can imagine building your first, decently sized prototype was a massive step. I've seen the footage, and it did look incredibly dangerous. So my next question is the same. How did Finn manage to rope you into to all this? What was the story behind that?
Rope me into it. He could barely keep me away from it. So Finn and I first met at the University of Washington. As he alluded to, we were both broke grad students when we started the company in January of 2020 with terrific timing. But we were working on this project together for several years even before that, when we met each other first at a professor-student pizza lunch, where afterwards he asked me about magneto-inertial fusion using hypervelocity metal shells around self-organized plasmoids. And I knew immediately that this is someone that I was going to have some sort of close relationship to. And so our interest in space travel, our mutual interest in space travel and advanced technology and nuclear topics like that kind of blossomed into this not only friendship, but working relationship. So Finn was working on the first iterations of the Jetgun launcher that he just ran off of 44 Magnum cartridges, shooting them off in his basement, pissing off landlords. And I got really excited by this tech because I saw the potential for it to be compact. I was also, at the time, thinking about the problem of decoupling the energy of launch from the launch vehicle in order to make space launch more efficient. Because there needed to be a better way than rockets. So I identified the work that Finn was doing as, being this significant work, and just immediately joined aboard. And it was fun developing it, building bigger prototypes. I'm a physicist, so I have barely any practical experience. So Finn had to teach me like what a wrench and a screwdriver were. And it ended up being not just something that was technically interesting, but also personally gratifying.
Great. So I wanted to ask you about the defense applications. We touched on it with Finn, but a lot of the people watching this channel probably know that the launch market isn't doing particularly well right now. It's quite saturated, so it's probably not the best time to break into that market. So what you guys are planning on doing is going to the defense market first, to develop your technology further, get initial funding. So what are the defense advantages of your system? And I know you're not really able to make forward-looking statements as a company, but what could that potentially mean for the future of wave launch?
Right. So the decision to go into defense was partially motivated, as always, by the quest for funding. So classically, the Department of Defense has always been the first person in space projects. If any of your viewers or yourself are familiar with the SBIR program, a great deal of companies don't just get SBIR grants from NASA or National Science Foundation. A good chunk of those SBIRs are funded by the Department of Defense. So the Department of Defense is always looking for future technologies that could give them an edge in any of their combat domains. It just so happens that the Jetgun was more suited for ground combat than it was for use in space launch. And I think that while annoying to work on two separate technology streams, it is actually a blessing for our company. The majority of launch companies have absolutely no product that they can sell outside of just their rocket launches. And we actually see this becoming a problem with several launch providers such as Astra, where their launch service is becoming unsuccessful and they find themselves suddenly needing to pivot into other markets that may or may not be as successful. The defense market does not necessarily depend on the success of the space market. And as a relatively uncoupled market, we can continue to win contracts and to advance this technology. What makes the Jetgun particularly interesting and why the Department of Defense, the Navy, as well as prime contractors we've talked to are interested in it is because of how it aligns with the future doctrine of the United States Fighting Forces. So the United States Marine Corps, their commander drafted a doctrine known as the Force Design 2030 doctrine, which de-emphasizes heavy equipment like tanks, like artillery, like large ships, and focuses more on compact and agile systems. When you look at the Jetgun compared to a 155 millimeter howitzer, for instance, you can immediately see the size savings, the weight savings, and the cost savings, as well as this ability to now launch a variety of munitions, because instead of stuffing them into a barrel, you can just place them on top of this pusher plate Finn was describing and launch them off. So while I can't make predictions about the future of this technology, since military projects are infamous for getting canceled all the time, there's interest in using the Jetgun technology aligned with these Force Design 2030 doctrines and integrating it as a new weapon for long-range precision strike, replacing artillery and larger missile launcher systems. And if we could achieve that, that would be a substantial amount of revenue. Since BAE Systems has sold over 1,500 of their M777 155 millimeter howitzers worldwide, you can imagine that's the sort of scale of industry the Jetgun could potentially reach.
Yeah, that's amazing. So your initial plan is to go into defense, build up a reputation / improve the technology and gain revenue. But the long-term vision, especially for space launch, is this Macron Beam. So technology-wise, Finn, how does this differ from the Jetgun, and what sort of capabilities does it have that are unique to the Macron Beam?
Yeah, so I mentioned that the issue with the gas jet is that it dissipates, so you have a short acceleration distance and therefore a high acceleration. So the fundamental difference between a Macron beam and a gas jet is that the Macron beam is made out of these millions or trillions, quadrillions of tiny little solid dust particles all traveling together in a very dense stream at very high velocity. And the important property that such a stream has is it doesn't dissipate. So it'll punch right through the atmosphere and give us many kilometers of acceleration distance over which to push a vehicle up to orbital velocity. And that allows us to bring acceleration loads down to comparable acceleration to an ordinary rocket, which has this additional knock-on effect of being able to use everyone's payloads. We don't have to say, oh, it has to take 2000 G, or it has to handle these crazy vibration loads. It handles the exact same environment that a regular rocket does. The difference is that since we're now supplying energy and propellant from the ground, our structural mass fraction goes from about 2 to 5% on our launch vehicle to about 20 or 50%. And that has these huge knock-on effects on, construction, simplicity of construction, on the expense required for a heat shield, for instance. You get to that enormous mass fraction, you can start thinking about just having a tank of water instead of applying, ablative heat shields or ceramic tiles. So there's all of these enormous knock-on effects that make the launch much, much cheaper once you're supplying energy and propellant from the ground and you're at low acceleration levels.
So from a practical standpoint, how does that work when you're accelerating a vehicle from the ground, but the vehicle is already many, many kilometers into the air? How are you able to steer the vehicle? Do you sort of like point the nozzle like a sail? And how do you calibrate the types of accelerations you can get?
So if you're 10 kilometers away, 20 kilometers away, 100 kilometers away from your Macron beamer straight up, you're not going to be able to point your beam in a timely fashion. Like, you're not going to have like a control loop between the vehicle and the beam. Our intention here is instead to put all the control systems on the vehicle itself and make it try to follow the beam. And then for the acceleration level, this is pretty straightforward. It's just, you've got a certain mass of particles hitting the vehicle. They're going to cause a certain reaction force, which is your thrust, and then off the vehicle goes.
All right, great. So the Macron beam allows you to go fully to space and potentially beyond low Earth orbit to further destinations, right?
Yeah, absolutely. And that's one of the nice things about this, since you're not carrying the propellant with you, instead of having this tyranny of the rocket equation where your propellant mass relative to payload mass goes up exponentially as your delta V increases. Instead, your vehicle remains exactly the same mass, exactly the same payload mass fraction, regardless of how fast it's going, within reason, of course. So we could take advantage of this scaling within, low Earth orbit range. The cost advantage over rockets, at least, the aspirational figures expressed by Elon Musk's for his Starship system of $10 to $20 per kilogram. The cost advantage is not great. I think we're estimating $6, $7 a kilogram minimum from the Macron beamer. But once you get above low Earth orbit to lunar missions to Mars, missions to other locations beyond LEO, the cost advantage becomes greater and greater. It's just the difference between an exponential curve and your kinetic energy curve going as the square of velocity. The exponential curve very rapidly outstrips it in terms of the amount of energy involved, which for a mature transportation system is going to be your dog.
So assuming you're able to pull this off, what are the potential applications of the Macron beam longer term, James?
Right. So obviously we're focused on space launch now, and terrestrial space launch. So this idea of using a mass beam of pellets or particles isn't necessarily even new. People were exploring this as a method of interstellar space travel, of like pushing an interstellar spacecraft using particles going a fraction of the speed of light. That could be one far future use of the Macron emitter if humanity manages to get into the solar system. Looking a bit more down to Earth, however, the scale and power levels of the prototypes that we are constructing right now are such that they would be able to compete with various cutting tools in the machining and manufacturing industry. So we're building a desktop prototype that will start sending these particles to 3 to 5 kilometers per second, a fraction of what we need for space launch, but good enough to allow these particles to cut through pieces of metal, similar to how a water jet cutter or a laser cutter would work. But of course, with these microparticles, you can have much finer definition and detail because the width of your beam is now the width of these microparticles, the width of a human hair, essentially. So more precise than wire EDM while having the same power capabilities as water jet cutting. And the really interesting thing is that if you slow the particles down from that speed in our benchtop prototype, you'd be able to add material using the same device to the workpiece. So now you have a cutter that does not just cut, but can additively manufacture, can 3D print while you're working on the same piece using the same material. And so that represents one potential pivot if there's some issue with the Macron emitter that doesn't allow us to conduct terrestrial space launch in atmosphere. And then, of course, atmosphere being a problem, if you take the Macron out of the atmosphere and place it in an extraterrestrial environment where you have vacuum, now you no longer are worrying about drag on your particles. So there's a potential use for this technology in space mining, not necessarily in the resource extraction stage, but in the resource transportation stage. You can imagine lunar material or material from a large asteroid being processed into these macrons, fed into a beam. Instead of having a launch vehicle lift off from the surface of an extraterrestrial body, you can directly take the material and beam it across the solar system to spacecraft and space stations that would be able to process it and make it into materials for the in-space manufacturing and servicing economy. So those are a couple of applications that we've thought of that would allow this technology to work even outside of its intended Earth to LEO space launch application.
The Macron Beam isn't just like a tool for space launch. You know, if developed, it's a generalized tool not only for manufacturing but for transmitting materials and momentum throughout the solar system as needed.
Okay, that sounds good. It's a universal tool, basically, not just a launch system, which is a really interesting product system. So I guess with the terrestrial applications, it does give your company a bit more flexibility. If, you know, when you're developing a new, brand new technology like this, it's difficult to predict the direction things will flow. So you have options, which is really good.
Yeah, absolutely, Nathan. We definitely try to be dual use or triple use technology as much as possible, but we focus on the space launch aspect because it's cool and exciting. We would not be listed on our pre-launch on Space Ventures, for instance, would not be a thing if we were just saying, oh, we're making this really cool cutting tool.
As aspirational as space launch is, as a company, we're aware of the fact that we need to grow and survive. We don't have any investors currently, and the first we're doing was just with our graduate student salaries, our pocket money, essentially. So being not just a business that does cool things, but you to survive and function even on low budgets is a priority for us.
Of course, that sounds good. And with the wide array of potential applications for this Macron Beam technology, I think one of the most important things could be the intellectual property of anything that your company develops. So how far have you investigated on that end, and what types of patents do you think you could potentially accumulate in the future?
So with regard to intellectual property, the Jetgun itself is already protected by patent. So Finn has been issued U.S. patent number 10928146, I believe, for apparatus and method of accelerating a projectile via external free jet. And the list of claims in that patent is quite extensive. So the Jetgun technology is ready for commercialization and fairly protected. For the Macron Beamer, we are currently working on a patent. The key piece of intellectual property, as you can imagine, is how we accelerate those particles. You can't really patent a phenomena of nature, and the tendency of particles to self-organize and self-focus in a jet is exactly that. It's just a phenomenon that we're taking advantage of. But we are working on another patent to protect kind of that key piece of accelerating the particles in an energy efficient and compact way to hypervelocity, as well as using a variety of secrets. So our company, despite being young, we have some legal aid. We have NDAs for people to sign before they get deeper explanations of the technology. Working with the military, we have pretty good IT services that are able to keep files secure and things of that nature. So we are pretty focused on protecting IP, and we'll be papering some of those newer discoveries, patenting some of those key pieces of technology, certainly in the next few months. And again, there will be never patent, simply because trade secrets never expire as long as they're a secret.
Yeah, we're definitely keeping the feed system for the Macron Beamer a trade secret. It's pretty simple, but if you think about it, you want to feed millions, quadrillions of tiny micron-sized particles precisely into the beam lines for a Macron Beamer. That's not something that's easy and cheap. But we think, figured out a pretty easy and cheap way to do it, and we're not going to tell anyone about it.
Of course. So to wrap up this interview, I know that you guys are currently in pre-launch on the Spaced Ventures platform. We had Aaron Burnett on the channel a few weeks ago, and he designed his platform specifically for perhaps broke graduate students who have really good ideas, but not necessarily a way to get that initial funding to get off the ground to get something bigger like a military contract. So it seems like a lot of people on Spaced Ventures are interested in potentially supporting your company. So what is the next step, assuming that you do get funding from Spaced Ventures? Where does that go in the near term?
Well, that is going to go towards continuing to prototype the Macron emitter. I can say that any support we get, grants, or possible future investments, that is the next stage of development in our company, is that we're on a good commercialization path for the Jetgun technology with this Navy contract. But this more interesting, useful Macron emitter technology is something that we still need to develop and commercialize further before it can be reliably used as a product. And so that's going to be the big goal, is within the next year to demonstrate, especially making a matter beam, a Macron beam that can travel at the speeds 20 kilometers a second or so that we would need to achieve orbital launch. That would be the big milestone with any future funding we get.
Of course. Great. Well, I really hope that everything goes well with your near-term funding rounds and everything, even though I'm sure that 5 years from now, 10 years from now, one way or another, the company will be nowhere where you expect it to be, because developing new technologies tends to have so many surprises. But I do have faith that a lot of these surprises will be good for you, because all of the fundamentals do check out. As long as it's within the laws of physics, it's not only possible, but inevitable. And that's exactly where it looks like you guys are. So best of luck. It's so great to have you on the channel. You're welcome back anytime that you have updates on this incredibly innovative technology.
Thank you, Nathan.
Thank you so much, Nathan. Again, it was really great talking to you. I hope that you and your viewers learned a lot.
Of course, and I'm sure we did. So take care, and I will see all of you next time.